This video is on logical equivalence. We can use truth tables to determine whether or not logical expressions are equivalent. We say that two expressions are logically equivalent if their truth values match for each combination of true and false values for their variables. So let's start with an example. I'd like you to write truth tables for each of the logical expressions below, and then determine which of these expressions are logically equivalent to one another. So we've got P implies Q. We've done this one before, but I'd like you to make sure that you kind of know it from scratch. Not P implies not Q, and not Q implies not P. So write truth tables for each of those logical expressions and then compare to see which ones are logically equivalent. Grab a piece of paper, pause, and try that out. Okay, so P implies Q. If P is true and Q is true, then yes, P implies Q was true. If P is true, but Q was false, then a true thing implied a false thing. This would be false. If P is false, then the if statement being false means that we don't have to follow through and worry about the then statement at all. This is automatically a true statement if P is false. Same here. To help with our other two logical expressions, we have these intermediate helper columns, and so we know that not P just has the opposite truth values of P. So when P is true, not P is false, and when P is false, not P is true. Similarly, when Q is true, not Q is false. So there we go. And now not P implies not Q. So here we have a false thing implying a false thing. That's true. As long as the first piece is false, it's true. Here we've got a true thing implying a false thing. That's false. And a true thing implying a true thing. That's true. Next, not Q implies not P. So now we're going backwards. False, the first piece is false, and so this whole thing is true. Now we've got true implying false. That's false. Now we've got false, and because that first piece is false, that means the whole thing is true. And finally, true implying true. Yes, that is true. Now let's check for logical equivalence. So now when we're checking the truth values here, we see that this does not match with this. So not Q implies not P is not logically equivalent to P implies Q. These are not logically equivalent. Whereas if we check here, true, true, false, false, true, 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 true. All of those truth values match, and so that tells us that these two expressions are logically equivalent. And so we see that as we've written above, P implies Q is not logically equivalent to not P implies not Q, but P implies Q is logically equivalent to not Q implies not P. This is a special logical equivalence. We call this the contrapositive. So not Q implies not P is the contrapositive of the expression P implies Q. It is always logically equivalent, and we'll be using this significantly later on. So when we're doing a proof, sometimes if we're trying to prove a statement of the form if P then Q, it's actually easier to prove a statement of the form if not Q then not P. So this is a whole method of proof, and its validity is based on the fact that these two expressions are logically equivalent to one another. Here's another one to try. So I'd like you to write truth tables for each of these logical expressions, and then determine whether or not they're logically equivalent. So pause, write the truth table for each of those, and then we'll talk about it together. Okay, so these are the two expressions that we want to compare to one another. Here's just a helper column, the P and Q and R. So we'll do that to help us make this one. So P and Q and R, that's only true if P is true and Q is true and R is true. That's true here. But in every other case, there's at least one false. So if there's at least one false in every other case, that means we're false all the way down. And so that tells us that the negation of the entire statement, not P or and Q and R, is opposite of what we have in this column. So we've got false and then true, 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 true. Our last column, not P or not R, Q or not R. So this is true if any of those is true, not P is true, or not Q is true, or not R is true. So here, not P is false, not Q is false, and not R is false. So this is false. Here, not R is true, so this is true. Not Q is true, true. Not Q is true. Not P is true. And for the rest of the way down, not P is true. Now, we've got given the truth tables for each of these. Now we want to check, are these two expressions logically equivalent? False, false, true, 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 and so on. Yes, these are logically equivalent. So yes, we've shown that the statements or the logical expressions not P and Q and R is logically equivalent to not P or not Q or not R. Great. So here is one last one to try. Write the truth tables for P and Q or R, as well as for P and Q or P and R. And then check to see if they are logically equivalent. So pause, try that one out. Okay. So P and Q or R. So this is true if P is true and Q or R is true. So Q or R, this piece, Q or R is true here, and P is true as well. So true and true. Here, Q or R is true, and P is true. So true. Here, it's not the case that Q or R is true, so this whole expression is false. And then the rest of the way down, P is false, so P and anything is false. So false, 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 false. Now let's look at our others. I did helper columns for this other one. We're really interested in this, but we'll use these two to help us out. So P and Q, yes, P and Q is true. And P and Q, yes. Here, P and Q is false. And here, P and Q is false because Q is false. And then the rest of the way down, we've got false because P is false. And then in our next column, P and R. So here, R is true and P is true. True. Here, R is false. So this is false. Here, P and R are both true. And here, R is false. Now for the rest, again, P is false. So P and R is false. And lastly, putting those together, P and Q or P and R, this is true if either of those two pieces is true, or both. So this is true because P and Q is true. This is true because P and R is true. This is false because they're both false. And then all the rest of the way down, we've got false because both columns are false. So now we can compare these and see if they're logically equivalent. So we've got true, 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 and then false all the rest of the way down. So yes, these are logically equivalent. And we've shown that P and Q or R is logically equivalent to P and Q or P and R. Some logical equivalences are especially important in logic and in doing proofs. So here are some of those important logical equivalences. The first set is De Morgan's laws. So we actually already did this one above with truth tables. In fact, we did it with 3 variables instead of 2. So we showed that not P and Q and R is equivalent to not P or not Q or not R. So we've done this already for 3 variables, but it works for any number of variables. So De Morgan's law says that putting a negation out front switches the symbol inside. And that might be familiar to you in terms of sets. So you might recall that the complement of A intersected with B is equal to A complement union B complement. And this is the parallel idea. So this is De Morgan's laws for sets and De Morgan's law for logical equivalence. Similarly, we've got not P or Q is equal to not P and not Q. And again, that's parallel with the complement of A union B is equal to the complement of A intersected with the complement of B. So again, having the not either out front or over the whole thing switches the symbol in between the expressions. The contrapositive law is the first one we talked about at the beginning of this video. And as I said, we'll use it later as a justification for the contrapositive technique of proof. Distributive laws, P and Q or R is the same as P and Q or P and R. We did this one above, and then the other one is going to be a homework assignment showing that those two are logically equivalent, that P or Q and R is the same as P or Q and P or R. Again, this relates to sets as well. So, for example, A intersected with B union C is the same set as A intersected with B unioned with A intersected with C. So these same distributive laws for statements or for logical expressions also works for sets. Next we've got the associative laws. So these ones are like a little more obvious, I would say, that P and Q and R is the same as P and Q and R. The way that we associate those together doesn't matter. And similarly, A intersected with B also intersected with C is the same thing as A intersected with B intersected with C. And same deal for ORs or for unions. And lastly, the commutative laws. Again, these are pretty obvious, I think, that P and Q is the same thing as Q and P, and P or Q is the same as Q or P.